Welcome back, everyone. We're getting close to the home stretch here for this class. Um, I'm gonna upload homework 6 tonight. Homework 5 is due tonight. I have office hours, and I am really gonna try to get everyone's responses to or feedback on the intermediate report. I'm really going to try to get that done today. So hopefully that works out fine. Yeah, I think that's everything announcement-wise. Well, yesterday we took a little bit of a break and or looked at Python and Excel Solver again. Try to do those with a little more simplicity. Hopefully that was helpful. Today we're back talking about the last big application of duality. Is it the last? Am I wrong? Let me look at the schedule again. I feel like there might be another topic, but I don't remember exactly what it is. Yeah, so the last big application of duality is today. It's called sensitivity analysis. And then tomorrow we're going to talk about some topics or some ways to deal with multiple objective functions, which can be important. All right then. So let's get into this. So remember our complementary slackness condition. It tells us that somehow the dual variables and the slack variables are they're somehow interlinked. They somehow inform each other. So we're going to explore that a little more today, and it's going to give us a pretty powerful and I think pretty neat sort of corollary to how the simplex works and how duality works. That is useful when you're making business type decisions based on an NLP solution. So we're going to look at the Soylent diet problem again. This is our LP for that problem. And then all I did, what I've done is change the direction of two of the constraints by multiplying by -1 so that the dual is a little easier to see. And then I took the dual of it. And remember that each dual variable corresponds to one of the constraints in the primal. So our first primal constraint was we had to have a certain number of calories. Then we had to have at most so many fats, at least a certain amount of protein, and a specific volume. So I've marked out the dual variables to correspond specifically with specific constraints. So then, from complementary slackness, if we take a look at one of our constraints, we know that either the fat constraint is satisfied at equality, or the dual fat variable is 0. And having seen the optimal solution to this problem, we know that this is actually satisfied at equality for our optimal solution. So our optimal dual fat variable is in fact free. It can take whatever value. It does not have to equal 0 by complementary slackness. So let's look, and we wonder, can this dual fat variable tell us anything else? We know it's not 0, but can it tell us anything important about the problem, about the system, about our solution? So we're going to look into that a little bit. So I think the easiest way to see how this sensitivity analysis sort of relationship shows up is to consider the units of all of the constraints, or of all of the parts, all of the terms in our constraints. So when I say unit, I mean that each coefficient has it means something, right? If you've taken physics, you're familiar with unit sort of analysis and jumping between different units. And you know that both sides of this equation should have the same unit, because apples and oranges are not comparable. We can't compare two things unless they're in the same unit. So if one side, suppose, this is not the case for this problem, but suppose this was in dollars and this was in miles per hour when we evaluated the whole side, that constraint doesn't mean anything. So each side has to be the same unit. Let me work on this example and maybe you'll see what I mean exactly. So this 0.1 over 30 is the deliciousness index. I'm just going to abbreviate that as del. It's the deliciousness index of the first variety, but its unit is deliciousness. This negative 25 is kilocalories per cubic centimeter. And this is grams of fat per cubic centimeter. This is grams of protein per cubic centimeter. These are a little small to see. Let me write those bigger. This is grams of fat per cubic centimeter. And this is grams of protein per cubic centimeter. That's barely any bigger. And there is a unit sort of buried here, but it's just cubic centimeters per cubic centimeter. So I'm not going to bother writing that. So somehow this needs to evaluate to deliciousness. Somehow we need to assign a unit to our variables that lets us evaluate to a deliciousness index. Or actually, this is deliciousness per cubic centimeter. Yes. That makes more sense. So currently the left-hand side is something per cubic centimeter, and the right-hand side is deliciousness per cubic centimeter. And what we're going to do is we're just going to figure out what units we can assign to our variables to make the left-hand side evaluate as deliciousness per cubic centimeter, like the right-hand side is. So, for example, if we have, let's pick the first term. In fact, every individual term here needs to be in the same unit, in the unit deliciousness per cubic centimeter. So let's do a little algebra. Times something over, I'm going to call this A over B. No, I'm just going to say Y. Somehow that has to equal deliciousness over cubic centimeters. Well, we can multiply both sides by CC. Get the kcals times Y equals deliciousness. And divide. So Y is in terms of deliciousness per kilocalorie. And perhaps better, this is Y cal. It should have the unit deliciousness per kilocalorie. So deliciousness per kilocalorie. And using the same sort of logic, we can see that Y fat is deliciousness per gram of fat. And Y protein is deliciousness per gram of protein. And Y volume is just going to be deliciousness per cubic centimeter. We can see that by cross multiplying, well, we can see that these grams of fat, grams of or kilocalories, and grams of protein all cancel out, and we're left with deliciousness per cubic centimeter on the left-hand side. Which is what we wanted. And this may seem like some circular logic, but we know that this constraint means something because it's the dual of a primal problem that means something. So we know that this constraint is it is actually meaningful, and it should be logically consistent. So our units, when we find some units that check out, those have to be the units that each of those variables is actually in. That sounds circular, but it's really not. So what we can glean from this is that our y variables, our dual variables, they have a unit, and that unit is meaningful to the overall problem. And we'll explore that shortly. So let's look at the objective function real quick. This is kcals times deliciousness over kcals. That cancels. This is fat times deliciousness over fat. Fat cancels. This is protein times deliciousness over proteins. Protein cancels. This is cubic centimeters times deliciousness over cubic centimeters, so CC cancels, and we're left with minimizing deliciousness. Remember, in our primal problem, we were maximizing deliciousness, so in the dual, we are minimizing something, and we know that the two have the same optimal value by weak duality. So if they have the same optimal value, it makes some sort of sense that they should be on the same scale and they should be in the same unit. So minimizing deliciousness makes some sort of sense there. So as we've just said, the y-cal is in kilocalories per cubic, no, that's not right, is deliciousness per, I'm not being consistent, deliciousness per kilocalorie. Fat is deliciousness per gram of fat. Y protein is deliciousness per gram of protein. And the Y volume is deliciousness per cubic centimeter. So each of these puts some value on a unit of kilocalories, fats, proteins, and volume. Value to the resources how do I want to say this? The resources associated with each primal constraint. That's what I'm going to say. And I'm going to put value in quotation marks because it's a little bit of a flimsy definition, but it's useful for us. So if you remember this problem, we had to have a certain number of calories. We had to have at most a certain number of fats. We had to have at least a certain number of amount of protein, and we had to have exactly a certain volume. So what these dual variables, what their optimal solution tells us, is going to be how valuable having extra fat allowance is. So I'm going to say y star, I'm going to do it in purple, y star fat tells us how valuable an extra unit, or an extra, in this case, gram of fat would be. Or better yet, in this case, how much well, let me make this statement twice. Tells us how much an extra gram of fat would increase the objective, or the deliciousness of the current basis. So let me demonstrate that by dipping into Excel. Screen capture, Excel. Okay. So here is yet another slightly different way to write up the Soylent Diet problem in Excel Solver. And I've done this so that the dual, if I click on the dual sheet, it changes very little. I'll explain that shortly. But what I've done here is I've solved it as it comes, standard. And then I have bumped up the fat by 1 unit, the fat constraint by a single unit. And I've solved it again. And I have subtracted the two objective function values. So in the primal here, we have this objective function value. When I add an extra gram of fat to the constraint as an allowance, I get a new objective function value. I subtract them to find this difference. I think there's been some rounding, so let me format that cell. Yeah. 1075269. You can't see that, but it's rounded up from 1075269. And then I solved the dual. And I noticed that the fat, y fat, has the same number as our difference between the two different solutions. So that's really neat. So our idea that y put a value on fat allowance seems to work. It seems to be true. So our dual variable indicates how much increasing the right-hand side of that constraint helps or changes the objective function value of that current basis. And that basis, the word basis is going to be important in a second. This number here, if you ever see e to the negative like 13, 14, 15, 16, it is probably a round off error, and so it is effectively 0. Treat that as 0. It's just a numerical error. It's below the machine precision of Excel. If you don't know what that means, don't worry about it. Just treat that as 0. And then what I did is I increased the fats by 15 units. So we're up to 35. We can have 35 grams of fat in our mixture. And then I took the difference again, and then I divided it by 15 because that's how much I increased the fats by. So, and that is the same number that we just saw in the +1 gram and in the dual y fat variable value. So even up to 15 extra units, we can see and the same amount of increase in our objective function value. But if I bump it up to +16 grams of fat, we actually put ourselves in a different basis. And we don't actually utilize all the fats because it's not optimal. And so we're not getting the same amount of increase. Well, correction, we are getting exactly the same increase if we see these two cells. Exactly the same increase over the original problem. But we have an extra gram in this new one. So once we get to the point where the current basis becomes infeasible or suboptimal, we might see a different pattern emerge, and suddenly our shadow prices, which by the way is what our dual variables indicate, shadow prices don't match up anymore. Also, if I subtract a fat from the original problem, the current basis that we were at earlier becomes infeasible, or the optimal basis for the original version of this problem is infeasible, and so we have to pick a new basis, and we don't see the same sort of shadow price relationship here. We have a different amount of decrease. And then I did the same sort of idea with the calories. So I increased the amount of calories by 500. Let's look at the dual. The dual variable for the calories is 0. And that comes from complementary slackness. if we look at the slack variable for the primal problem associated with the calories constraint, we see that it is positive, which means that the dual variable has to be 0, like complementary slackness. And that indicates that we're not actually tight to our calorie constraint. So changing the amount of calories that we have to play with may not, or it doesn't, change the basis. Let me draw that in the lecture. So again, we call the values from the dual constraint shadow prices. So if we had, suppose we had a two-dimensional problem. And we had this constraint and this constraint. But this was the optimal solution. Notice that we can move this other constraint. We can move it around and not change the optimal solution. We can perturb it a little bit. Suppose they were both pointing inwards, so this is the feasible region. We can perturb that somewhat until we get to where it intersects the optimal solution. And then suddenly, if we move it past that, it becomes infeasible. On the other hand, if we are to move the constraint that it is tight to, a one where the slack variable is 0, that will move the optimal objective, or the optimal solution, and it could increase or decrease the objective function value of that optimal solution. So that's sort of the relationship we're seeing here. And the shadow prices, i.e. the dual optimal solution, tells us how much that increase or decrease is. And again, if it's not tight to a given primal constraint, the dual variable for that constraint will be 0 by complementary slackness. And changing that constraint around, perturbing it, adding or subtracting a little bit to the right-hand side doesn't change the optimal solution or the optimal objective function value. So, what then? Let's go back to here, back to our Excel file. And look at one additional piece of data. One extra solution. In this one, I added to the volume. I let us have a little more volume. And we'll look at the dual. The volume has a shadow price of 0.00597. But when I added a volume, I got a different difference. And that's because the deliciousness it's an average, and so it changes with the volume. And so this sort of relationship is not strictly linear. So we have a little trouble there. And it doesn't quite work out. So this kind of analysis doesn't always like averages because they're not necessarily linear, depending on what you change. But we can get, so one of the neat things about Excel, one of the things I really like about Excel is that we can ask Excel to print out shadow prices for a given solution. You'll see it after you run the solver. There's a box in the upper right corner that I didn't take a snapshot of and show you. Let me do that actually. I think I can do that real quick. Yeah. A new snip. Pop. And then I will add a screen capture of the snipping tool. So yeah. Done. So over here in the over here we can ask for a few different reports. If you click on sensitivity and then press OK, it is going to print out something that looks like this. A new workbook, new worksheet, and it has our shadow prices. It has a lot of information about the problem, about the optimal solution, and about the shadow prices, and a few other things that we'll touch on here in a second. The one we've talked about so far is the shadow price column. It gives us the final value for each constraint, and the right-hand side of that constraint, and the shadow prices. And again, we'll see that if the final value and the right-hand side don't equal, they're not equal, the shadow price is 0. So if our constraint is not tight to the solution, the shadow price for that constraint is 0. And we can see that that's the case for the calories and the protein. But the final value, or the shadow price for the fats, is here, and it's positive. And since this is a maximization problem, a positive shadow price improves the solution. Now this is where things get confused, because on the tableau we're looking for negatives on a maximization problem. But on this page, the reduced cost is negative. I'll define reduced cost in a second. And the shadow prices are positive, which would mean a positive improvement in the objective function value. So that is that screen. We'll come back and look at that again in a second. I want to jump back into the lecture slides and talk about a few other things. Yep. So now we've defined shadow prices. And we want to, why is that blurry? Hello. Okay. We're going to talk about reduced cost real quick. The reduced cost is just the objective function row in our tableau. So if we had remember we have a tableau 1, 0, sum A, and then we have the objective function and then the right hand side and then the B vector. When we put that in the canonical form for a different basis, we call this area the reduced cost. I'm not sure whether the book defined it or not earlier, but that's what reduced cost is. And we notice that, remember from our proof from strong duality, that the optimal dual solution was given by AB inverse transpose CB. If we look back at our tableau equations, which I think are given in the tableau lecture. They are given in the tableau lecture, but they're also given in the simplex part 1 lecture. They're the canonical form. They're the negative of the canonical form equations. This is the reduced cost equation from the tableau. We notice that this is just y star transpose. So we have this. If we have a dual optimal solution, then the reduced cost for the optimal basis, this only works for the optimal basis. The reduced cost is a function of the dual optimal solution. Which is maybe not surprising because we've done a lot of this. I've pointed out a lot of these kind of similar relationships, but it is neat and it is very useful. Because let's say that xj or xi is the jth slack variable of the primal problem. So xi is a slack variable, and it's a slack variable we added to the jth constraint of the primal problem. Then ci is 0 because it's a slack variable. It doesn't have any location. It doesn't contribute to the original objective function. So its objective coefficient ci is 0. And the reduced cost of xi can be given like this. So this is just the vector is the ith column of A. It's a vector. And we already said that Ci is 0. So we could ignore that. That's Ci. And then we look at the ith column of A. The ith column of A corresponds to a slack variable, which means that it's going to be, because remember, A is the original A matrix to the original problem. The ith column is a slack variable, so AI, or to keep the notation straight, AI is an elementary vector, which you may remember. It has zeros everywhere except for the jth entry. And I know it's the jth entry because I said xi is the jth slack variable. So this is just a notation. It's the elementary matrix with entry j, where 1 is in the jth spot. And a vector times that is just going to pull out the jth element of the y vector, y star. So we're left with the jth slack variable. The reduced cost of the slack variables is equal to the shadow price of the corresponding constraint. The shadow price, or the dual variable optimal value, is the shadow price. That's crazy. Let me show you this in Mathematica. This is my Tableau printing program. Again, for the same problem we've been looking at, the Soylent diet problem. And I've pivoted it to the optimal basis. I did not include the slack variable for the volume constraint because the volume constraint is not present, or it's not a, excuse me, it is an equality. So the slack variable is always going to be 0. So it doesn't commonly show up in the tableau. And in fact, it could throw a wrench in the works if you tried to include it in the tableau. But we see that the slack variable, the second slack variable, which is the slack for fat, has a reduced cost that is the same as the shadow price we picked up earlier. And in fact, it's the same as the optimal dual value for y fat. So this points out something really spectacular, I think. And that's the tableau encodes both the primal and the dual in one compact table and with relatively simple operations. The tableau of the dual is actually just sort of the transpose and then flip of the tableau of the primal. That's what I find neat about this. But what's useful about this is we have our shadow prices in the tableau right here. So if you are doing the, if you are creating Soylent Green, or if you work for the Soylent company and you're trying to create these pastes, you want to sell more Soylent. I think we're in the Soylent yellow, blue. No, Soylent red is X2. You want to analyze your Soylent and you're saying, hey, in this context, this deliciousness sort of context, if we could convince people to eat a little more fat, they're going to buy more Soylent, or that their optimal meals are going to include more. Hold on. This analogy is not quite working, is it? Let me try again. So you're the passenger on the ship. You're the child who wanted to put together his or her or whatever their optimal, their most delicious meal. And your mother says it can't be over so much fat. It can't be over 20 grams of fat in that meal. But you tell her, if I could have just one more gram of fat, it would be this much more delicious. You can make that sort of argument. The book has a good explanation of what the shadow price means for a production type problem. If you're producing chairs, actually let me just go down and show that example off already. This is the optimal tableau for the assignment problem that shows up in section 1.2, I think. It's a gross tableau, lots of fractions. But here we see that if I could have a little more of resource 1, which I think is time on machine 1, then I could improve our overhead by this much. I could improve our profit by that much for 1 extra unit of time on machine 1. Let me find the problem exactly so I can explain this. we're not using all of machine 2 already, so we can find increasing the amount of machine 2 time that we have available won't actually change our bottom line, our profit. S3 is a slack in the amount of skilled labor. Well, S6 is this constraint. It says that the amount of unskilled labor, we can only hire 650 unskilled labor hours. If we could increase that to say 700, we might have a better optimal solution. So let me just try that real quick. See what happens. 700, yeah. So we've increased our profit by letting us hire more unskilled labor. What about 800? Yeah. I assume that's higher. Nope, this is infeasible. Actually, 700 was infeasible too. Yeah, so that's the next thing we need to understand is how much can we actually change these by, these constraints by, before we become infeasible, or before we have a different basis that's optimal. What can we do? And the answer there lies in the amount of slack, or in the slack values. So if we come back over and look at Excel, the Excel sensitivity report shows off an allowable increase and allowable decrease for each constraint. If we look at the primal problem, we see that the slack in that constraint, our first constraint, is actually equal to the allowable decrease. Here, because this slack is originally a less than or equal to constraint. So the slack would be added to the function. So our allowable decrease, because I negated the constraint, our allowable decrease becomes the allowable increase before infeasibility strikes. Maybe that made some sense. So let's go back here and keep increasing the amount of calories that we could have had. So I added 500 to make it 2,000. Well, let's get the primal. Let's grab this. Nope. Oh Lord. Equals 1,500 plus this number. And then solve it again. Oh, this should be negative. Solve it again. We get that the same basis, and in fact the same optimal solution, holds with the same objective function value because the reduced cost for, or the shadow price for the calorie constraint was 0. But if I subtract 1, or correction, yeah, I wanted to subtract 1. So if I add, what? Confused. No, I subtracted 1 to this. That's the wrong one. If I subtract 1 here, probably... There we go. I have a negative slack, which means that it's infeasible. Our current solution is infeasible. So I run the solver again, and in fact, the solver couldn't find a feasible solution at all this time. So we do have to be careful when we're talking about sensitivity, shadow prices, because we can only increase things so much sometimes. So let's look back at this sensitivity report. The allowable increase here was 15 for the fats. Remember, I leveraged that. I bumped it up to 15 over what we had. And then when I bumped it up to 16, we were in a different basis. And the sensitivity or the shadow price no longer held. And this again comes from the slack variables. And depending on the direction of the inequality. This 1 plus e to the 30, that's again a machine error, machine precision. That's the biggest number that Excel here is able to comprehend of, so that's effectively infinity. So that's what all of these things mean. That was a lot of explaining and a lot of different concepts. And I think tomorrow I will put together another example and talk about the specifics of the sensitivity analysis of that problem. And then, of course, we'll take any questions anyone has. Yeah. That's all the content I have for today. So you guys are free to go. Naturally, I will stick around and answer questions.